Okay, hello and welcome to a brief introduction to quantitative analysis, or a brief introduction to statistics. This is SOC224, and this is the lecture for weeks 11 and 12. So let's get straight into it. In terms of the concepts this week, I know. First of all, this material is late, and secondly, that you are overwhelmed with other work. So I'm going to say the only stuff that I actually want you to understand this week is the stuff on the left-hand side here. Descriptive statistics, inferential statistics, these four terms, and correlation coefficient. The ones on the right, the t-test, the linear regression, and I'm briefly going to touch on logistic regression. That's not going to be examinable, and I'm giving it to you simply as so that you get a good education, so to speak, but you don't need to worry about it for the final exam. So let's get straight into it. When we talk about statistics, it turns out that there are two main classes of statistics. There's descriptive statistics and inferential statistics. Much of what you would have experienced in, say, high school is what's called descriptive statistics. The purpose of that is of descriptive statistics is to summarize a group. So it's things like a mean or a median or a standard deviation. And why do we actually have descriptive statistics? Well, we use it because it helps us reduce the amount of information we need to think about a particular group or a large number of people or units or whatever it is. So, I've got the example on the slides here. Try to visualize 4,000 people's ages without thinking about an average or a distribution. It's just impossible. You can't hold, even for 25 people, it's very hard to hold in your head the ages of 25 members of a group or 100 members of a group, and to think about them all at the one time. You can for a family of 5 people, but you can't for numbers over about 10. And so what descriptive statistics allow us to do is to come up with a few numbers to summarize the many. In particular, the big ones are to have a mean, which is like an average. It's called one of the central tendencies of a group of numbers, and then a standard deviation. And if you've got a mean and a standard deviation, then you know that about 95% of people within a group will lie either within 2 standard deviations above and 2 standard deviations below that mean, assuming it's normally distributed. So that's the point of a descriptive statistics. It allows us to summarize and simplify groups. However, inferential statistics are quite different. When descriptive statistics describe a group that you have got and you can measure, inferential, coming from the word infer, which is to know something about something that you can't directly observe, for inferential statistics, our goal is to draw a conclusion about a larger, unseen population based on a smaller sample of that population. So why do we do it? Well, we do it because for 2 reasons. Right? One is we want to know about large groups of people. We want to know about the 27 million people in Australia, or we want to know about the 7 billion people on the planet, or the 300 million people in America, or the billion people in China, or whatever. I think it's the 1.3 billion people in India. We want to know about those larger populations and be able to say something about them. But it is incredibly expensive to actually survey all of them. When you survey all of a population, it's called a census. These are done, as you know, the Australian census was last done in 2016. But these are incredibly expensive exercises, and often they only capture a limited range of characteristics. So Yeah, so that's why we sort of need to use a sample to draw conclusions about the larger populations. How do we do it? Well, we're going to go through a bit of it today, but honestly, it's much more than what we can do in this class. So, look, there are more complicated mathematics, but the main principle it uses is the idea. Well, it asks, what do we know about the true population parameter? A population parameter being some characteristic of the population, given the information we have in this sample. You conduct various significance tests, which tell you the estimated probability that the population parameter is 0. We'll go into that in more detail. It'll make more sense. What are some examples of it? Well, any measure that's got a standard error rather than a standard deviation, or any measure that has a significance test or a p-value, you're in the realm of inferential statistics. Okay, let's go into descriptive statistics a little bit more. So the most commonly used descriptive statistics are the mean, a standard deviation, the minimum value in a group, the maximum, and the number of valid cases. The mean tells us the central tendency. The standard, so approximately where is the center of this group. Standard deviation tells us about the variation within the sample. Minimum and maximum tells us the range of values. And the number of valid cases tells us the sample size. And so if we happen to have a number of valid cases, or an n, for a variable that's lower than the others, which we'll see later, it means that there's lots of missing data. Maybe lots of people didn't answer the question, or maybe they weren't eligible to answer the question. So, yeah. Okay. Inferential statistics, these are a few important terms and concepts. So, in inferential statistics, we draw a strong distinction between the population, which is the group you're drawing inferences about. So that might be Australian voters, or people in China, or people in America. And the sample, which is a set of cases you have to analyze that is assumed to be drawn by a true random sample from the population. Say a sample of 1,000 voters surveyed by phone. So you have the population, which is unseen, but the group you want to know about, and the sample, which is randomly drawn from that population, and which you use to make inferences about the population. Okay, then we have two numbers. The first is the population parameter. This is the true value in the population, which you're trying to estimate. So this might be, well, I've given it here, the mean age of Australian voters. The thing about the population parameter is that you know it exists, but you don't know what it is, unless you've got something like the Australian census. But in generally speaking, we don't have it. So what we have, the population parameter, is this mythical object that we want to almost mythical object that we want to try to estimate. And then our estimate of it is what's called the sample statistic. So this is the number you calculate on your sample in an attempt to estimate that population parameter. So it might be the mean age of your sample of 1,000 voters. Okay, fine. That's pretty straightforward. So population, sample, population parameter, sample statistic. These are parallel concepts. Okay, now in any of you who have done statistics will be familiar with this and probably have got very confused. We have this idea in statistics of the null hypothesis. this is, and I'm roughly speaking here because I'm trying to give you a sort of like statistics without maths, and without too complicated ideas. But the null hypothesis is roughly speaking the idea that the hypothesis that there is nothing happening. And that in relation to most statistical tests or most population parameters that you may be estimating, because you'll be estimating things like the difference of two means. Is there a difference in means between men and women when they in the number of working hours they do? Now, the null hypothesis is almost always that the population parameter is 0. And this is what you're trying to, if you can disprove this hypothesis or show that it's very unlikely, then the effect will be that you have sort of shown that there is something happening. So that then leads into our next concept of a p-value or statistical significance, which roughly speaking is the chance that our population parameter is 0. This is expressed as a number between 0 and 1, and its critical value is p less than 0.5. Sorry, 0.05 or 0.05, which equates to a 5% chance, or a less than 5% chance, that our population parameter is actually 0, or whatever our null hypothesis is, but that's generally it. So we may say that, for example, if we were looking at the number of hours worked by men and women, and we asked, and we found that the p-value was less than 0.05, that means that there was less than a 5% chance that men and women were working the same number of working hours on average. Okay, so our confidence interval then is the range within which we expect, normally with a 95% confidence, that the population parameter lies. So let's just go back to our example that I'm using of men and women working. Let's do men and women doing housework. So we do a survey of 50 men and 50 women, and we find that the men do 5 hours and the women do 10 hours on average per week. Now, we're trying to estimate the population parameter, which is the true difference between these two, between men and women, which we don't know. We have using a concept before, the sample statistic of the averages was 5 and 10. So the sample statistic in this case will be 5, which is the difference. The difference between 5 and 10 is a 5. So 5 hours of work, 5 hours of domestic work per week, and then we may find that the p-value is less than 0.05, but the confidence interval is between, say, 2 and 9, right? So that means that 2 and 8, I should say. So that means that we don't know exactly what the true value of the population parameter is. We don't know whether it's 3 or 6 or 8, or even it could be higher. But we're 95% confident, based on the tests and the statistics we've calculated and the nature of the sample, that it lies between, say, 3 and 8. That's an example of a confidence interval. Okay, so let me run through a brief example of descriptive statistics with a data set which is kind of funny and fun and interesting. I choose this deliberately so that it keeps your attention. So this is a data set actually collected by my students. It was of pornography consumption by students in Singapore. It was 595 respondents, all students. It was approved for use for teaching by the ethics committee at the university. It's called the Institutional Review Board. The data has been anonymized. It's actually available online on methods101.com under SPS Intro Practice Datasets. And what we're going to do is just calculate the descriptive statistics. So the first thing you do is go to Analyze Descriptive Descriptives, and then then you push across into the variables box here all the ones you want to calculate. And now let's take a look at the output from SPSS. So this is a descriptives table that comes out in the output window. And you can see here we have N, which is the number of valid cases, minimum, which is the minimum value, maximum, mean, and standard deviation. Let's look through some of the things that you can immediately see here. So have you watched porn? It's either a 0 or a 1, and 86% of people said that they had. Okay, fine. Number of times you've watched porn. This says a missing coded 0. You basically ignore that. That includes everybody. It just means that those who said they never watched porn were coded as a 0. Again, 596 N and minimum 0, maximum. That is a very specific maximum number. This is in a month. This is the number of time watching porn in a month. So it's like about 10 times a day. And the mean is about 10 times a month. Okay, but there's a large standard deviation, so there's a lot of variance in that number. We've got a few other questions here. These are questions like, how much are you aroused when you watch porn, or how disgusted are you when you watch porn? And it goes from 1, which is basically not aroused at all, to 7, which is highly aroused, or 1, which is not disgusted, and 7, which is disgusted. You can see the values here, so they're above average, above the center point for arousal, but not for disgust. Gender, 1 is female in this case, so 40% of the sample is female. Relationship status, 1 is in a relationship, so 58% are in a relationship. Relationship satisfaction, so we can see here that, well, look here, this is a good example of why descriptive statistics are important. So the N for relationship satisfaction is only 252. Why? Because there's only 252 people who are actually in a relationship. So only the people who answered relationship status positive then answered this next question. Most of them are pretty happy. And religiosity, everyone answered it, and they were a bit religious, but not super religious on average. Next, we're going to deal with correlation. And so that was all just descriptive statistics. But we're going to now start dealing with concepts that use inferential statistics a lot more. So let's do the first one, correlation. All right, so most of the time, social scientists are interested in relationships between various different characteristics. We've just seen the recent federal election, and in that we saw that there was a swing against or towards Labor in wealthy areas and away from Labor in lower socioeconomic areas. That is a relationship, a correlation between socioeconomic status and changes in voting. And as social scientists, that's one of the main things that we're interested in. But how do you measure that? How do you measure a relationship between two variables? Well, the main way, or one of the main ways, is called the correlation coefficient. A correlation coefficient, you can, and I think on the right, let's just look on the right here at some of the examples just of what are the different types of correlation. So this is a strong positive correlation. So as one thing goes up, the other thing goes up. So, you know, as if we had electorates here, and we had the number of wealthy people and the number of wealthy people along the bottom here, and the number of people voting Labour, or proportion, switching to Labour, the swing to Labour, then we'd have a positive correlation. This is a negative correlation. We can also have a weak and a moderate relationships where the points are much less clustered together, and no relationship looks something like this. It just is sort of a random set of points with no relationship between x and y. Okay, so what is a correlation coefficient? It's a number between 1 and -1 that indicates the strength of a relationship between two variables. 1 indicates that they completely covary in a positive direction. So something like this is almost a 1. And -1 indicates that they completely covary in the opposite direction. So an example is something like this. And then 0 indicates they're statistically independent. So that's something like this here. So this is going to be a 0, this is going to be close to 1, this is going to be close to a -1. Okay. Now, often we get a number and then we're trying to know, is it big or not? So these are very rough ways to interpret effect size. They're not absolute, but I think they're useful. So things like a small effect size is around 0.1 to 0.2, plus or minus. And a medium effect size is around 0.3 to 0.4, and a large one is around 0.5. One concept which we'll learn about more in linear regression is that it turns out if you square that number, so if you multiply it by itself, then you get the proportion of variance of one variable shared by the other. It's like, well, what the hell does that mean? Okay, let me give you an example. It's actually an amazing concept. If we multiply 0.5 by 0.5, what do you get? 0.25. That's a proportion, 0.25, which is actually, as a percentage, we can say it's 25%. If we had two variables that had an R squared of 25%, what we could say is that approximately 25% of the changes in, say, your dependent variable are potentially explainable. You can't say they're actually explained, but they're potentially explainable by your independent variable. This is quite a powerful thing, and it allows us to put real numbers and real sort of weights to various explanatory factors. Yeah, but we'll do some more on R squared in a sec. So this is what a series of different Pearson's correlations look like. So 0 looks like nothing, 1 looks like not much, 0.2 looks like a bit, 0.3, it's okay, 0.4, again, it still looks like a bit of a blob, you know. 0.5, a little bit less of a blob. 0.6, we're starting to look more like a line. 0.7, a real line. 0.8, yep, looking great. 0.9, 0.95, 1.0. We see here that actually even relatively high correlation, remember this is this is a strong correlation at 0.05, still involve a huge amount of noise and other things going on. Okay, so this table is constructed because you will hear, particularly from psychologists, but many people, statisticians, that there are lots of different correlation coefficients, and Pearson's is not always the right one to use. And this is true. This is definitely true. However, as you'll see on this table, in many cases, Pearson is pretty much is the right one to use. So if we have interval level variable correlated with interval, or interval Likert correlated with Likert or interval, then, or with binary, then we use Pearson. The only exception is when you have ordinal variables with many or few ranks. Then you've got two other options that you probably are going to need to use, which are the Spearman and Kendall's. My main point here is most of the time it's fine to use Pearson. It's a good, here we go, lesson. It's generally most of the time the correct one to use, and if you're not sure, then go check a textbook or Google. Okay, let's do an example of Pearson's correlation. So we go to Analyze, Correlate, Bivariate. We'll push across not all of them, but some of the variables. And this is what it looks like. A few things to notice. There is a significant weak to moderate positive correlation between arousal and the number of times watching porn. So here we go. So number of times watching and sexual arousal on watching porn, 0.28, and see the significance. See that 0.0000? Well, that means it is less than 0.001. That's anyway, but SPSS doesn't report p values lower than that. We can also see there's a negative correlation with watching porn and disgust. There we go, minus 0.292. And also being female. Gender is 1 for female. So if you have a 1 for this, you'll have a lower value for number of times watching porn, which is fine. And then no significant relationship between religiosity and number of times watching porn. So here we go. Whilst you may have hypothesized that religiosity matters, it turns out that it doesn't. So here we have a Pearson's correlation. The correlation is 0.04, so tiny, right? And the significance is 0.289, which is way above 0.05, so it's not significant, and it's quite small, so we just ignore it. Okay, next. Now that's up to this point. That is everything that's going to be in the exam and that's examinable. The rest of this is just relax and enjoy it. You may want to use it for your projects. You may want to use it in some future research. You may read about it one day in an article, and because of that, I want to introduce it to you. So up next, we're dealing with t-tests. So a t-test is a test used to compare the mean value of a dependent variable in two groups. So I think we're going to give the example later of comparing the amount of pornography watched by men and women. Generally, these two groups are an experimental group and a control group, but they don't have to be. They can be, like, for example, two demographic groups, or you could split any variable. You could just split variables. Everyone over the age of 28 and under the age of 28 and below, or something like that. Now, there are two types of tests. There is what's called a paired samples test. This is when we say do a t-test on the same two people. When we do a t-test on two different measures on the same group of people. So yeah, there's examples of, I think in the textbook, of the emotional states of people when they are listening to death metal and when they are not listening, and maybe listening to classical music. This is an example. We maybe have 100 people and we have a measure of these two things. So we have 200 measures we're comparing. We use a paired samples t-test because the statistics are slightly different. Each of these cases is not independent of one another, but actually has got the same people, and so the statistics is different. Just leave it at that. An independent samples t-test is when we have different individuals. We're comparing two groups. So if we're comparing men and women, that's an independent samples t-test. If we're comparing a group of sociology students with a group of business students, that's an independent samples t-test. Okay. When we do an independent samples t-test, SPSS outputs a Levene's test, and when you get, and we have to interpret this to know which row of the output to interpret. The rule is if the Levene's test is significant, then we read the column for equal variance not being assumed. Sorry, the row for equal variance not being assumed. If it's not significant, then we read the row for equal variance being assumed. You'll see what I mean, I think, in the example. I think I'm not going to talk about this, but basically yeah, I'll just leave it. So, example. So we go to in SPSS, we go to analyze, compare means, independent samples t-test. And then when we're in independent samples t-test, we push across the test variable, which is our dependent variable, and then we've got to put a grouping variable. So I put gender in here, and we have to hit define groups, and I've specified the values 1 and 0 as the two different groups. And hit continue, and then I'll hit OK, and we get the following output. So this is if we look here, we can see, so females are 1, males are 0. So we have 239 women and 357 men. And what do we have here? The mean number of times watching porn is, for women, is about 4 times per month, and for men it's about 13 times per month. So then we go to the independent samples t-test. Now, that, if we just to show you, 13 minus 4 is actually over here, this mean difference, which doesn't change. The mean difference is 8.944. 8.9, basically. And the question is that significant or not? Well, we have to, because it's an independent sample, we have to do Levene's. I've misspelled it in the last one. It's L with an E, not A. Levene's test for equality of variance. It is significant. 0. So let's go back. What does that say? If it is significant, then equal variance is not assumed. That's good. So equal variance not assumed, the bottom row here. We go across. Look, it's still significant, so it doesn't matter. But there's a slight difference in the confidence interval. So this is our confidence interval. The true parameter value for, if we are based on a lot of assumptions which we've already violated, right? Because this is not some random sample. This is a convenient sample. But anyway, like roughly speaking, assuming that all the other things we've violated don't matter, then the 95% confidence interval for the difference between men and women, for the true population parameter, is somewhere between minus 11.9 and minus 6. So we know the true population parameter, so that like the true average difference between men and women and the amount that what number of times they watch porn in a month is in that range of basically 12 to 6 to 12. Very good. Okay, so linear regression. Now we're really getting into the big kids stuff, big kids statistics. So regression. What the hell is regression? Regression. This is a summary, and then we'll go through it in detail. So, regression is a model for predicting the value of one variable from the value of other variables. So, linear regression is a continuous variable that's being predicted from the value of other variables, and logistic regression is binary dependent variable being predicted from the value of other variables. In a linear regression, we use the equation of a straight line. So we say y, which is our dependent variable, equals this equation, which looks awful and complicated, but actually it's not. But it is the x1 is the value, and x2 are the values of various variables in your model. B0 is an intercept, and B1 and B2 are how much you multiply those values by to get the outcome. Okay, and that is, we'll get to it, and I'll make it make sense. It has some basic assumptions that the outcome is continuous, the predictors are not categorical, and the relationship between x and y is linear, and the samples are independent. Now, let's go through it in a little slightly more slowly. You actually learn the model for linear regression in about year 8 maths, right? Because in year 8 maths, you will learn the equation for a line. And I'm pretty sure if I asked you, you could probably still say it, y equals bx plus c, right? And what does that mean? It means that y, the vertical axis, equals bx, which is b is the slope of the relationship between x and y, and plus c, and c is the intercept. Yep. Well, that's basically what we do with linear regression, but we do that where x and y are real important characteristics in the social world that we want to try to understand the relationship between. So, and this is the way of expressing what we've just talked about. So bi, or b1, is the regression coefficient for the predictor, or it's the gradient of the slope, and it's the direction or strength of the relationship between x and y. And b0 is an intercept, and it's a point at which the regression line crosses the y-axis, or when x is 0, y equals b0, right? So our outcome is equal to b0. Let's look at some examples, and it will start to make more sense. So this is, remember, this is an example of outcomes with the same intercept. Sorry, models with the same intercept but different gradients. And these are examples of different linear models where the gradients are different, but the gradients are the same, but the intercepts are different. We can test the proportion of variance accounted by the regression model using R squared, which is very similar to the Pearson's correlation coefficient squared that we've been learning about earlier. It's easier to understand all this, however, if we use an example. So let's go through. We're going to go through a couple of examples actually. So let's say that there's a record company boss and they're interested in predicting album sales from advertising. They have data from 200 different album releases, and they have the outcome variable, which is sales or CDs and downloads in the week after release. This is a bit old. I mean, it needs to be Spotify plays these days. And then the predictive variable is the amount spent, this is in pounds, set in Britain, spent promoting the album before release. Right? So this is your X and this is your Y. So here we go. X is advertising budget. So 500,000 pounds, 1 million pounds, 1 million pounds, 2 million pounds, etc. And this is album sales, and what is it? In the week after release, in thousands. So 100,000, 200,000, 300,000, 400,000. We can see here that this is a graph produced by SPSS, and notice it's already put. This is actually the regression line. This line here. It's put the regression line in, and it's also calculated the R squared already. So that says that 33% of difference in album sales of actual albums is explained by the advertising budget. Notice here you can actually also just see a few things. So what does the intercept of this line, where is it? It's about, zero is about here, so it's about what, 150,000 album sales. So that says that if you do no advertising, you'll make about 150,000 advertising in advertising sales. Right? So no advertising, on average, you'll still sell 150,000 records. So how do we actually calculate this in SPSS? So we go to linear regression, and then we put in our dependent, we put album sales, and in independent, we put advertising budget. We click OK. We will get, firstly, this model summary, which simply tells us the R squared and the adjusted R squared. Look, basically the R squared is the percentage variance explained in the sample, and adjusted R squared is in the population. So the adjusted R squared is the proper one to really quote most of the time. And then these are the output of the model parameters. This looks all a bit scary, but the key things to do when you're reading an output like this, the first thing to do is go boom to the significance. Is it significant? So it turns out both of these are significant. And if so, then you read the unstandardized coefficients. So what does this say? This says the constant is 134, and these are in thousands. 1,000, which means that when there's a zero advertising budget, I said it was 150, it turns out it's 134. When there is no advertising budget, these records still sell about 134,000 records. And then for every 1,000 pounds spent, every 1,000 pounds of advertising budget spent, there is another 0.09. This is measured in thousands, 1,000 album sales, which is basically, well, what is that? What's the 0.096 times 1,000? I think that is 96. So there's basically 96 more records. So you spend 1,000 pounds, you sell another 96 records on average. Okay. And so we can then express this as an equation, B0 plus B1 times advertising budget, and this is basically what it looks like. Okay, so album sales equals fine. This is substituting in, so if we spend $100,000 on advertising, we'll sell about 143,000 albums. Fine. That's linear regression, and it's just where there's one predictor and one outcome, one independent variable, one dependent variable. The next thing we're going to do is learn about what's called multiple regression. So multiple regression is when we use a linear regression model to predict the value of one variable, but multiple regression is where we extend this to having several predictors. So let's just do an example. This time we're adding in numbers of plays on the radio and also the attractiveness of a band. Now what we can do here is you can do a matrix scatter plot. This is explained actually in the SPSS guide on methods101.com. What you can see here is the key one is the album sales and the relationships. You can see there is a positive relationship between each of these different things. The attractiveness of the band, the number of players on the radio. So it'll be interesting to know which of these are most important. Because in a sense you can see there's a positive relationship between all of them. And so it's not clear which is the cause and which is the effect and which is the most important. Okay, so multiple regression as an equation. We just make it expand the equation, so we just add in more and more predictors, basically. It's the B0 is still the same, but then we have the B1 and B2, etc. Bn are is the slope of the relationship between each of these other variables and the outcome. This actually doesn't make it any easier, but let's just look at a model and it will make sense. Okay, we've got to go through an example. Briefly, we're just going to talk about when you have multiple predictors, you need to decide how to enter them, right? Now, the main way you do it is just put them all in, which is called forced entry, breaking into your house, right? You just put all the predictors in at once. There are two other methods. Hierarchical is where you put a few in, and then you put a few more in, and then you put a few more in, and you decide what order to put them in. Stepwise is when you use basically a computer program to determine which ones go in and out. If we can go through these methods briefly, which one should you use? Hierarchical is pretty much the best method. The way it generally works is you put in the you firstly run a model which is what most other people think is going on, and then you run the model with your new variables. It's the best method because it's based on theory testing. But it relies on you knowing what you're doing, so it's sometimes bad. Forced entry adds them all in at once, and it's pretty good, but you still need to have reasons why you've put all the variables in. Lastly, stepwise is generally a bad idea. It can be fine for exploratory work, but generally if you need to do or you're thinking of doing stepwise regression, you don't actually know what's going on and you haven't thought enough about your topic before you get started. Yeah. Slight differences can have an effect on highly correlated variables, and these can have big theoretical differences. Okay, so let's run our model. So in linear regression, we have dependent variables, the same. We put in number of plays, and then we're going to enter various, we hit the next button basically, and then we can add in various variables. So here we go. This is the output of the model, and I'm just highlighting here what you should look at. We have model 1 is the original model we ran. It's just the advertising budget as the predictor of advertising budget as the predictor of album sales. So we've already seen that. Now let's see what happens once we add in the other variables. I think attractiveness of the band is based on like I have 1 to 10 attractiveness scale or something. So for every point of attractiveness of the band, they sell another 11,000 albums. That's hilarious. And it's highly significant. The number of plays on the radio, so every time it's played on the radio, they sell another 3,000 albums. Notice here the constant has dropped to minus 26, which is like, what does that mean? Well, what that is, sometimes for in regression models, the constant is really the value of the outcome if all the independent variables are set to 0. But in many cases it's impossible or that they'll be set to 0. So for example, I don't think there would be any bands that have an attractiveness of 0, right? So it doesn't make sense. What you have to do then is you really only interpret this within the range of the real values of these. You still report it as this model, but you don't say, oh, you don't take this as truly meaningful. The other one just to note here is that so if we look at significance, that's not significant. Why? Well, because the constant actually includes 0. So the upper bound and the lower bound of our 95% confidence interval goes from minus 60 to plus 7. And so we can't be confident that the true parameter value, the population parameter, is, we can't be confident it's not 0. Okay. You can see here the confidence intervals for each of those different unstandardized coefficients. So each coefficient is a change in outcome associated with a unit change in the predictor. Standardized beta values, so there's these things here are standardized beta values. You can think of these as these are basically numbers that are, I don't want to say, they're kind of indicators of effect size, which means they're indicators of how much impact these various variables have on the outcome. They are these values, but they're all standardized, so they're put onto the same same units of analysis. Okay, so that's our final. This is our model. When you report it, that's a bit ugly, but anyway. Okay. So there are various assumptions here. Some of them are straightforward, like that the outcome must be continuous and the predictors are continuous, and the relationship is linear in reality, and there are independence values of the outcome come from different people. But there are more tricky assumptions, which I'm not going to go into, around the fact that your predictors need to not be highly correlated. The error terms should be constant across different values of the predictors, and the errors shouldn't be correlated across pairs of observations. And also there should be normally distributed errors. But anyway, let's go back to our watch pornography example. And so we're going to go analyze, regression, linear, and then we go linear, then we put our dependent variable under number of times watching porn, and we're going to we're doing it as two blocks, so we're doing gender and religiosity first, and then we're adding in sexual arousal and disgust. Our idea being that we'll look at first like what the effect of gender and religiosity is on watching porn, and then we'll see what happens once we control for attitudes to these attitudes of arousal and disgust. So, very briefly, let's start looking at the model summary. We can see model 1 with just gender and religiosity explains about, well, let's see, the adjusted R squared, about 6% of the frequency of watching porn. And the second one is once we include arousal and disgust, it goes up to around 13%. What do the actual models say? So remember, the first thing you do is look at the significance. Religiosity is here not significant. So in this first model, religiosity has no significant effect. So just note that it's positive, but it's still not significant. And gender, as we know, is negative, so women watch nine women, which is a 1, watch about 9 less, what do you call it? Watch porn 9 less times per month. With a constant here of 11, so that would be sort of men would, this is, because the religiosity still has an effect, these numbers are a bit different to the other ones, but in this model, men watch 11 times, women watch twice. If we change it and we go to model 2, then and add in these attitudes, the idea here is that that it's really people's attitudes, not their gender per se or religiosity per se, that drive things. If we add these in, then all of a sudden our constant becomes non-significant. So fine, it's just, but it's still 5. And then here, gender, much less effect. It's only minus 3.8. Let's come back to that. Disgust, clearly negatively correlated. So, the more disgust, for each unit of disgust, a person watches porn 2 times less per month. And for each unit of arousal, they watch about 1.7 times more per month. But look here, religiosity has become significant. And so remember that religiosity is measured on a 1 to 7 scale. So religiosity, for each 1 to 7 unit of religiosity, someone will watch approximately 1 more time per month. Why? I've got no idea. And why does it become significant once we control for these other factors? Again, I'm not super sure, but yeah, I'm not super sure exactly why. But that's the fun of regression models. You throw in various controls and then you get unexpected results. Okay, we're just going to briefly touch now on the very last model. The type of models we could run, which is called the logistic regression. This is grad school stuff, but I'm just going to touch on it because it does end up being used in a lot of academic papers, and it is kind of useful if you have a binary outcome. So if you're trying to predict something so this is used all the time in the medical literature, right? Death or not, survive. I don't mean to be, this is a bit sensitive, but there is cancer survival statistics out there. 5 years survival statistics. There's effects on reducing the chance of heart attack by eating margarine rather than butter. All these sorts of things. These are almost always modeled as logistic regression models. And they have to be logistic regression models for two reasons. One is because they have a binary outcome. It's sort of like people who have had a heart attack or not had a heart attack, people who have survived or not, or people who got cancer or didn't get cancer. And secondly, because they are required to control for lots of other factors. You can't just model something. You need to. You can't look at just the bivariate correlation between a treatment and an outcome. You need to control for a whole lot of other things that might have reduced or increased various people's chances of survival or not. So, if you have a binary outcome and you have multiple predictors, you want to do a linear regression. This is the model which looks terrible, right? You're like, oh, that's freaky. But actually, the reality is, if you zoom in and look at this, what's in this, in the brackets here, to the power of the e to the power of minus this, it is just a linear model. And it turns out that really, ultimately, this is just a linear model with a bit of complicated maths, doing some conversions on the, transforming your binary outcome. But anyway, so you can think of them very similarly. This is how it becomes when you have multiple predictors. This is an example of it. So we have 113 adults with a medical problem. People are cured and not cured. Treatment or no treatment. We get, these are our R-squared values that are reported. We often report either one of these, Cox and Snell or Nagel-Kirk. They're sort of similar in interpretation to a adjusted R-squared or an R-squared. And then we get this model. Again, we have a constant, and then we have an intervention. This is our predictor. We have a b, and we also have an exponential b. Generally, we report this exponential b, which is called the odds or an odds ratio. And the odds ratio is the odds of the unit change in the predictor divided by the original odds. Basically, if your odds ratio is greater than 1, then the probability of the outcome occurring is higher. And if your odds ratio is less than 1, as the predictor produces a lower chance of the outcome occurring. So in this case, our intervention increases the chance of the person being cured. This is how we might report it. And I'm not going into odds ratios and so forth because it's a little bit more complicated, though if anyone is interested, I can share with them more details. Or you can also read through the textbook. I've covered the material for 4 chapters of the Andy Field Discovering Statistics Using IBM SPSS Statistics package, the 4 chapters that are in the unit guide. But I have covered them relatively briefly and hopefully simply. If you want more information, Andy Field is the best textbook in the world by far. There's also a lot of resources online which you can find with things like Google. And lastly, there is the website we've created, methods101.com, which has got a lot of resources on there for you. Okay, thanks. Bye.